Today we learn how to multiply two binary sign digits, okay, by using the Booth's algorithm. So let us start the Booth's algorithm. That is, Booth's algorithm gives a procedure for multiplying binary integers in signed 2s complement representation in a efficient way. That means it requires less number of addition and subtractions, okay, and it operates on the fact that strings of zeros in the multiplier requires no addition but just shifting the zeros and the ones, okay. So what is the Booth's algorithm? That means, as in all multiplication scheme, Booth's algorithm requires examinations of multiplied bits and shifting of the partial products, okay. That means prior to shifting, the multiplicand may be added to the partial product, subtracted from the partial product, or left unchanged according to the following rules. So this is basically the Booth's algorithm, which is based on the following three rules. What is the first rule? Rule number one is, if the multiplicand is subtracted from the partial product upon encountering the first least significant bit, that is 1, in a string of 1's in the multiplier. So this is the rule number 1. And in the rule number 2, the multiplicand is added to the partial product upon encountering the first 0, okay, that provided that there was a previous ones in the string of zeros in the multiplier. And in the third rule, that is, the partial product does not change when the multiplier bit is identical to the previous multiplier bits. So first of all, in the rule number 1 and rule number 2 and rule number 3 will be discussed in the next slides briefly, okay. That means now here we elaborately explain the rule number 1. That is, first we set the accumulator, that is AC, and the append bit qn plus 1 are initially 0, okay. So we set the values of AC and qn plus 1 initially 0, and the sequence AC is set to the number of bit, that is number, that means AC is set to the number n equal to the number of bits in the multiplier. That means basically the bits are used in the multiplier, okay, that same number of bits will be used in the count of SC. So the value of SC depends on the number of bit used in the multiplier, okay. If the number of bits in the multiplier used 4, therefore the value of SC is 4. If we use the number of bit in the multiplier 5, that means the value of SC is 5, okay. Next, the very important judgment is there, that is, the 2 bits of the multiplier in qn and qn plus 1 are inspected first, okay. What is the qn plus 1? Qn plus 1 initially we set to 0, and what is qn? Qn, that here qn means the mr, that is the multiplier, okay. So the least significant bits of the multiplier is set to qn. The least significant bit of the multiplier is set to qn, and initially qn plus 1 are set to 0. So if 2 bits are equal to 1 0, that means if the value of qn is 1 and if the value of qn plus 1 is 0, it means that the first one in a string has been encountered, that this requires subtraction of the multiplicand from the partial product in the AC, okay. So if it is 1 0, then what happens? If it is 1 0, then we apply the subtraction operation, okay. And if 2 bits are equal to 0 1, what does it mean? 2 bits are equal to 0 1, that means if the value of qn is equal to 0 and if the value of qn plus 1 is equal to 1, it means the first 0 in the string of the zeros has been encountered. So here we require the addition of the multiplicand to the partial product in the AC. So this is very important, the judgment, that is, if the value of qn and qn plus 1 is 1 0, then we apply the subtraction, okay, subtraction operation we apply, that is, we subtraction of the multiplicand from the partial product in the AC. And if it is 0 1, that means if the value of qn is 0 and qn plus 1 is 1, okay, then we apply the additional operation of the multiplicand to the partial product in the AC. And this is the third rule, that is, when the 2 bits are equal, that means if the value of qn and qn plus 1 is either 0 0 or 1 1, that means when 2 bits are equal, the partial product does not change, then we do not need to change the partial product, and overflow cannot occur because the addition and subtraction of the multiplicand follow each other, okay. So as a consequence, the two numbers that are added always have a opposite signs, okay. The condition that includes an overall the next step to be shift right the partial product and the multiplier including the qn plus 1. Okay, so this is the arithmetic shift right operation which AR, that is AC and QR. Okay, and the right and the leaves the sign bit in the accumulator unchanged. Okay, the sequence counter is decremented and the computational loops is repeated n times. So this is basically the procedure of the third step. If the bits are same, that means the qn and qn plus 1, the two bits are same, then we just apply the arithmetic shift right operations and we decremented the SC, okay, by 1, okay, until we have the some unchanged bit, okay, some unchanged, that means some changed bit between the qn and qn plus 1. So let us describe this in terms of flowcharts. So in this flowchart, this is basically the flowchart of the Booth algorithms. So the description that was described in the previous slide will be explained in the terms of flowcharts. Okay. So first, in case of the Booth algorithm, we have two things, that is multiplicand, that is MD, and multiplier, that is MR. Okay. So initially we set accumulator 0. We set SC, that means the number of bits stored in the multipliers, the same number of bits stored in the SC. So initially we stored that means initially set the SC 0 and the value and the highest value of the SC depends on the number of bits used in the multiplier. Okay, and initially accumulator is 0 and SC is 0 and qn plus 1 also 0. So initially we set these three terms 0 and then we check the values. They inspected the values qn and qn plus 1. So initially the value of qn plus 1 is 0, we know, and if the value of qn is 1, the least significant bit of qn is 1, then what happens? Then this is 1 0. If it is 1 0, then we apply the AC plus MD dash plus 1. That means we subtract the multiplicand from AC. So here we do the 2s complement of the MD. Okay, so AC plus MD dash plus 1. If it is 1 0, then we apply the subtraction operation of the MD from AC. And if it is 0 1, that means if the value of Qn is 0 and the value of Qn plus n and Qn plus 1 is 1, then we apply the additional operation, that is SC, that is AC plus MR. MR is the multiplier. If it is 0 1 combination, then we add MR, that is the multiplier, with the accumulator. Okay. Next we check one more thing, that is if the value is equal or not. That means if the value is not equal, that means either it can be 0 1 or it can be 1 0. But if it is equal, that means both the value, that is qn and qn plus 1, either 0 0 or qn and qn plus 1 1 1. So if it is both 0 0 1 1, so we use the arithmetic shift right, that is ASHL, arithmetic shift right, okay, between the accumulator and the qn, and we decremented the SC. And also after finishing these operations, if it is 0 1, then we apply SC plus MR and then we shift arithmetic shift right operation and decrement the SC. Again for the 1 0, by after applying the AC plus MD plus 1, okay, we apply the arithmetic shift right operation and decremented the SC. So this is the way we continue the process, and at last we check whether the value of SC is 0 or not. If the value is not equal to 0, then we again use the same, we repeat from the initial step, and if it is 0, then we end the procedures. Okay, so this is the basic flowchart of the Booth algorithm. So let us solve a problem by using the Booth algorithm based on this flowchart. So in the there is a numerical problem where we do the multiplications between the -5 and -7. So here what is the multiplicand? The MD, that is -5. So here the multiplicand is -5 and the multiplier is -7. Okay. So first of all we know that is multiplicand, that means MD, that is -5. So we make it in the binary term, that is 1 0 1 1. And what is the MD? MD is the 1 0 1 1. We know. Okay. And we do the 2s complement of MD. Okay. That is 0 1 0 1. And what is the multiplier? That is -7. We know. And we convert it into the binary digit, and the digit will 1 0 0 1. Okay. So now what happened in the first step? That is in the first step we know qn plus 1, that is 0. We set qn plus 1 0, and we also set AC that 0. That means here we use the 4 bit, because here the multiplier, in the multiplier we are using 4 bits, that is 1001. Okay, so in the accumulator that is 0, we using the 4 bit. Okay, and we know what is the value of SC, the highest value of SC. That means the number of bits used in the multiplier. That is how many bits are used in the multiplier? 4 bits. 1, 2, 3, 4. So here SC is equal to 4. So now let us check the, now let us inspect it, the value of Qn and Qn plus 1. So for the Qn, we check the least significant bit of the MR. The least significant bit of the MR is 1. And what is the value of Qn plus 1? Initially 0, we know. So what is the value? That is 10. If it is 10, then we subtract the MD, that is the multiplicate, from AC. Therefore, we add AC with the 2's complement of the MD. So AC plus MD dash plus 1. Okay. So we have done the 2's complement of the MD, which will be add with the AC. Okay. So after solving these calculations, okay, which gives AC as 0 1 0 1. So initially AC is 0 0 0 0. So after adding AC with the MR, after adding AC with the base complement of the MD, that means 0 1 0 1, will got, that is the value of AC is set to 0 1 0 1. And on the right shifting, that is now we apply the arithmetic shift right between the AC and MR. Therefore, the value of AC will become now 0 0 1 0, and the value of MR will 1 1 0 0, and the Qn plus 1 will be 1. And this whole scenario will be shown in the figure in the next slides. Okay. So initially we know AC is 0 0 0 0, and what is the value of MR? That is 1 0 0 1. And what is the value of Qn plus 1? Initially 0, and what is AC? 4. So we know very well this formula. Now we apply. Now we check before applying. Now we check the value of the Qn and Qn plus 1. Qn plus 1 we know 0, and what is the value of Qn plus 1? And this significant digit of the MR, that is 1. If it is 1 0 1 0, then we apply what? AC plus MD dash plus 1. We know MD dash plus 1 value from the previous slide. Just we add with the AC and got 0 1 0 1, and this value is same, that is 1 0 0 1, and this value is same, that is 0, and there is no change of SC. Okay. Now we apply the arithmetic shift right. So this 0 will come here, and this 0 will come here, this 1 will come here, and this 0 will come here, and this 1 will come here, and this 1 will come here, this 0 will come here, and this 0 will come here, and this 1 will come here. Actually shift arithmetic shift right for all the bits. Okay. And it is decremented to 3. The AC is decremented to 3 after applying the arithmetic shift right. Okay. So now we check what is the value of Qn and Qn plus 1. Now it is 0 1 combination. If it is 0 1, then we add MR, that is multiplier with the AC, and store the value in the AC. So now it will become 1 1 0 1. Okay. We know the value of MR and we know the value of AC. We just add the both and got 1 1 0 1, and this is same, that is 1 1 0 0, and this also same, that is 1, and there is no decrementing in the AC. After applying these rules, we again apply the arithmetic shift right. So when you apply the arithmetic shift right, then this one will come here, and this same 1 will come here, and this 1 will come here, and this 0 will come here. This 1 will come here, this one also will come here, this one is shifted here, and this 0 is shifted here, and this 0 is shifted here, and we decrementing the SC by 1, so it will become now 2. Okay. Now we check the Qn and Qn plus 1. Now it will same 0 0. Therefore we do not need to add or we do not need to subtract. Therefore we just apply the arithmetic shift right. Again after arithmetic shift right, this 1 will come here, this 1 also will come here, this 1 is shifted here, and this 1 is shifted here, this 0 will come here, this 1 will come here, and this 1 will come here, and this 1 shifted here, and this 0 is shifted here, and the SC count will decremented to 1. Okay. In the previous it was 2, and now it will be 1, because here we apply the arithmetic shift right. Okay. Now we check again the same procedure is there until it will become, the SC value will become 0. It is 1 0. So if it is 1 0, then we apply the AC plus MD dash plus 1 as per the previous rule. Okay. So now it will become 0 1 0 0, and this is the same, that is 0 1 1 1, and the value of Qn plus 1 is 0, and there is no change. Now we apply the arithmetic shift right. If we apply the arithmetic shift right, then this 0 will come here, this 0 will come here, this 1 is shifted here, and this 0 will come here, and this 0 is shifted here, and this 0 here, this one will come here, and this one will come here, and this one will come here, and it is now decremented to 0. Now the value of AC is 0, and we stop the process here. So what is the result? The result is accumulator and the MR. Okay, therefore the product is calculated as follows. The product is equal to AC M1. What is the value of AC? That is 0010. And what is the value of M1? That is 0011. So now we convert this binary digit into the digital number. That means this is 0, 1, 2, 4. Okay, like that. Therefore, what is the value of this? That means 0, 1, 2, 3, 4, 5. Therefore, this is 2 to the power 5, that is 32, and this is 2, that is 34, and this is 1, that is 35. Okay, so 32 plus 2 plus 1, that is 35. And obviously, we know when we multiply minus 7 with the minus 5, then we will got 35. So this is the result, and we solve the process. We solve the multiplications by using the Booth's algorithm this way. Thank you all.